In this video, we're going to discuss integrands with vertical asymptotes, which is our second type of improper integral. This occurs when the integrand has a vertical asymptote. So for example, this graph has a vertical asymptote at x equals 0. So this represents an infinite discontinuity, potentially. A limit of integration at some point between the limits of integration. So if we consider this function that we're looking at and we say we want to find the integral from 0 to 1 of 1 over the square root of x dx, we have a problem because the function isn't defined at 0. We cannot ever touch 0. So this is a situation where we end up having to use the value a. So we would solve this integral and we would get 2 square root of x, and we would have 1 to a, which simplifies to 2 minus 2 square roots of a. So then what we have to do is we have to look at the limit as a approaches 0 from the right-hand side of that integral from a to 1 over the square root of x dx, or rather the limit as a approaches 0 from the right of 2 minus 2 square roots of a. And of course, as you look at approaching square root of a, as you look at approaching 0 from the right, that's going to go to 0. So my output value here is 2. So therefore, we can surmise and we can say that 0 to 1, that integral, which was improper because the function is not defined at one of my limits of integration, that's the same as writing the limit as a approaches 0 from the right for the integral from a to 1. My integrand, that is equal to 2. So type 2 occurs where we have a discontinuity or a vertical asymptote occurring somewhere on our interval, our bounds of integration. So let me define type 2. So here's our definition for dealing with improper integrals of the second type. If we have a continuous function on some open interval, and maybe it's discontinuous at that a, then we have to look at approaching a from the right. And if it was discontinuous maybe at b, we would have to look at approaching that b value from the left. And if the discontinuity occurs somewhere between a and b, some point c in the middle, we have to break it into two integrals. All right, in each case, if the limit exists and is finite, we would say it is an improper integral which converges and that the limit has the value of the improper integral. And if the limit does not exist, then the integral diverges. So let's look at one example. So here we're going to investigate the convergence of the integral from 0 to 1 of the integral 1 over 1 minus x integrated with respect to x. As always, we want to think about, is there a vertical asymptote? Is there a discontinuity? We always, especially when we're dealing with area and convergence and divergence, we want to be able to visualize what that space is. So we create a graph. Now, what we will recognize is that as we approach 1, we're going to have a vertical asymptote. So that means this graph is getting closer and closer to 1 and increasing forever, but it's never actually going to touch that x equals 1 value. So this is like part 2 of our definition, and the function is continuous on the interval from 0 to 1. It is discontinuous right at x equals 1. So we can't verify this at x equals 1. It becomes infinite, as x approaches 1 from the left, my y values are becoming infinitely large. So in order for us to evaluate this integral, we would go to part 2, and we would rewrite this and say, well, this is the same as the limit as b approaches 1 from the left-hand side. My integral is now going from 0 to b, and we're dealing with 1 over 1 minus x dx. Now this is easy to integrate with a u substitution. Let u equal 1 minus x, du equals negative dx. So that would turn my integral into negative 1 over u du, which is negative the natural log of u, and plugging my x value in, that would be negative natural log of the absolute value of 1 minus x. So I'm dealing with the limit as b approaches 1 from the left. I don't know why I put an extra little 1 there. As b approaches 1 from the left of negative natural log of the absolute value of 1 minus x, evaluated from b to 0. So as we continue in this problem, I'm going to deal with evaluating my definite part of the integral, and then we'll do the limit as our last step. So the limit as b approaches 1 from the left of negative, I've got the natural log, the absolute value of 1 minus b, minus negative natural log of the absolute value of 1 minus 0. So right here, I've got the natural log of 1. The natural log of 1 is 0, so minus a negative, that would be plus 0, but we just know that part is going to go to 0. So I'm dealing with the limit as b approaches 1 from the left. Again, I did that again. I got a little extra negative in there. We've got negative natural log of absolute value of 1 minus whatever my b value is. So at this point, we want to evaluate this limit as 1 approaches from the left. And if we think about that value, a value of 1 from the left, maybe b being something very, very close to the left, or close to 1, but still to the left of it, then if I plug that in here, 1 minus 0.99999 gives me a very, very, very small number, right? Very small. That number is approaching 0. And I just can't write today. So really what we're thinking about as we plug that value to the left of positive 1 into our function, we end up with negative the natural log of something that is very, very small, but still positive. So we've got a very small positive number. And as we think about taking the natural log of a very small positive number, that's going to give me negative infinity. So this ends up giving me a value of positive infinity as my integral value. The area under the curve is divergent. It does not approach a single number. All right. So, and just thinking about the graph of a natural log, as the argument becomes smaller, then the log becomes very large in the negative direction. So essentially what we were doing right here, we were thinking about the limit as x approaches 0 from the right of natural log x. And that is going to equal negative infinity. So the negative was already in front, negative, negative becomes positive. Doesn't matter, it does not converge to a single value. We cannot find the area under this curve. It is divergent.